Hi everyone. Today I'm going to talk a little bit about the Chapter 5 test format, what to expect there, and then talk about the first part of Chapter 6. So starting with the Chapter 5 test, I think we're going to keep the test date scheduled as quoted before on Monday. So the Chapter 6 or the Chapter 5 test will have start with 3 required questions. So the first question will be like finding trig functions using a reference triangle or identities. Either one is fine. And then you'll have one solving question. On those solving questions, there's something you can use the unit circle to do, and one simplifying question. So just like the first, 3 sections of the homework sets. And then you're going to get 8 trig identity proofs. You only have to do 5 of them. You can pick whichever 5 you want. They're not going to be ordered in difficulty. Typically, the proofs can be done in 2 to 4 steps if you choose the most efficient route through them. So you may need more to do them, but none of them are going to be are supposed to be full pagers. They're all weighted the same, so just do the ones that that you see the route for seem the easiest to you. And then make sure that you indicate which ones should be graded and which ones should not be graded. So don't leave anything just blank. Just put like a big X through it or fill out the not grade box or whatever. Okay? So that's the Chapter 5 test format. So Chapter 6 is about this. We're going to give you guys a new set of trig identities. So if you look under this Chapter 6 stuff, I've already posted that new identity sheet. So the first 3 sets of identities are things that we've already done. And then we have these 4 new sets of identities. So you have sum and difference identities. We're going to talk about those today. Double angle identities, power reducing identities, and half angle identities. So we're going to start talking about these sum and difference identities. So we're going to start by deriving one of these sum or difference identities geometrically. Now this is something that I'm going to do just for the sake of doing it. It's not a process I would ever expect you to repeat. But let's say that we have 2 angles on the unit circle. Actually, let me do this. Let's say we have some angle here that I'm going to call V. So that point there is going to be cosine V, comma, sine V. And then I have another angle. Let's call that over here, call that one angle U. So the point there is cosine U, comma, sine U. And then let's say that then the difference between those angles is going to be this theta. Okay? And I guess for the sake of argument, let's name that point A, that point B, and we'll call this the origin point O. So what we're going to want to do is we're going to take that angle theta, and I'm going to start by, oh my goodness, come on now. Whatever. Translating it so that it's in a standard position. So say it's here, right? And I'm going to call that point then A prime. Now, why would I do that? Let's do that. And so that point is, coordinate is cosine theta sine theta. Okay, so we have here that theta is equal to v minus u. I'm sorry, u minus v, So, we know a couple of things here. So we know that this segment, AB, and I guess I'm going to give this, call this point B prime or whatever. And this segment, A prime, B prime, are the same length. And again, that coordinate on B prime has to be 1, 0, because this is a unit circle we're working on. So the radius is 1, so that x coordinate has to be 1. So we can say then that AB has to equal A prime, B prime. So the length of segment AB has to be the same as the length of segment A prime, B prime, because that angle theta is the same size, because to get the second picture there, we just translated that angle theta so that it was in standard position. We just picked it up and moved it, so one of the arms of our angle lie on the positive x-axis. Okay, so everything is the same. So those segment lengths have to be the same. So I'm going to use the distance formula then to calculate this. So remember, the distance formula is, like the x-coordinate for B minus the x-coordinate for A squared plus the y-coordinate for B minus the y-coordinate for A squared, square rooted. And we can say the same thing about A prime, B prime. Right, so this is just me writing down the distance formula again without plugging anything in. So we know that those two equations are equal. So I'm going to square both sides to get rid of the square roots. So I can do like one of these. Okay. And then let's go ahead and substitute the values from our equation. So the x-coordinate for B was, in our case, we'd had cosine U. And the x-coordinate for A was cosine V. And similar here. Oops, except these are sines. And the x-coordinate for B prime was 1. And for A, it was cosine theta. And the y-coordinate for B was 0. And the y-coordinate for A is sine theta. Okay. And then I'm going to go ahead and FOIL all this out. So we're going to have cosine squared u minus 2 cosine u cosine v. Through the magic of editing, I've gone ahead and expanded that all out. Oops. It's plus. So now I take a look and I see, okay, well, I have a cosine squared u and a sine squared u. So that's 1. I have a cosine squared v plus a sine squared v. That's 1. And then on the other side, I have a cosine squared theta and a sine squared theta. So that's going to be 1 also. And then everything else I'm just going to copy in. Oops. Okay, so far so good. If I subtract 1 from each side, and I do that 2 times, those can cancel out. If I divide both sides by -2, those will cancel out. So I'm left with cosine u times cosine v plus sine u times sine v is equal to cosine theta. And if we remember, we said that theta was equal to u minus v. And I have my first identity. Okay, so if I go back and I look at my trig identity sheet, the way we've written these sum and difference formulas, we've written them as both the sum and the difference in one line. So what we just proved was cosine of x minus y was equal to cosine x times cosine y plus sine x sine y. So the way you read one of these things is the symbol that's on top here goes with the symbol that's on top over there, or if you're reading the symbol on bottom, goes with the symbol on bottom. So it's just a convenient way to, instead of writing 6 of these identities, we're writing 3 of them. It just compacts them together. Okay. All right. So to change this then to addition, what do? Well, I'm just going to use a negative value for v. And fill it in. Now, minus a negative just makes it positive. Cosine of a negative, if I look at my odd-even identities, is just cosine. But sine of a negative makes negative sine, so I'll move that negative out front since everything is just being multiplied there. And this is my angle sum for cosine. as we saw on the previous page. Okay. How do I do this for sine? Well, let's say sine of u plus v is equal to sine theta. I'm going to use my cofunction identity to rewrite this as a cosine. And then I can use my difference of two angles. Oh, no, I don't want to do that. That's going to be bad. I'm going to write this as u plus v. And then we'll distribute the negative through. And then I'm going to group these together as like one angle and apply my angle difference formula for cosine. So I'm going to have cosine of pi over 2 minus u times cosine of v plus sine pi over 2 minus u sine v. And I know that cofunction identity, that just turns into sine u. And that turns into cosine u. So I have my angle sum identity for sine. To get the angle difference, I'm just going to substitute a negative v in here and then push that negative through. You'll end up with the same thing. And then the last one is what do we do for cosine? Or I'm sorry, for tangent. So let's say we have tangent of u plus v. Well, that's just going to become sine of u plus v over cosine of u plus v. So sine of u plus v we have right above. And then cosine of u plus v is this. And if we really want to be technical, we probably want to get both of them at the same time. So let's make these, do the subtraction one at the same time. So that would be how we'd write that. But this version right here is probably not the version that we would be using in practice. This actually can simplify down. And you should recognize that piece that we boxed in yellow is equal to this that I'm just now writing, because I think this was the identity in the problem set for chapter, one of the identities you had to do in the problem set for chapter 5. I think it was like number 57 or something. Okay, so that's the 6 angle sum identities. Let's do some examples of the kinds of problems we're going to ask you to do. Okay, so some example problems. So the first one says find the exact value of cosine of 75. Notice that 75 is not a unit circle angle. However, we can still do this problem. All we need to do is think of a way to write 75 as the sum or difference, it doesn't matter, of two unit circle angles. To me, the obvious two that I would use are 30 and 45. So we'd say cosine of 75 is equal to cosine of 30 plus 45. Then we'll apply the angle sum formula for cosine. It's going to be cosine of 30 times cosine of 45 minus sine 30 times sine 45. Then I'll go to my unit circle and look up my values. So cosine 30 is root 3 over 2. Cosine 45 is root 2 over 2. Sine 30 is 1/2. And sine 45 is root 2 over 2. When I multiply these fractions together, I end up with root 6 over 4, and then root 2 over 4. So I'm just going to write these together as a single fraction as root 6 minus root 2 all over 4. That's it. So the next one, find the exact value of 5 pi over 12. The same idea here, except it's a little bit more difficult to see what unit circle angles we're working with when it's written as in radians with a fraction. So the observation that I'm going to make is that on the unit circle, the denominators for my angles in radians are either denominator of 2, 3, 4, or 6. All of those are factors of 12. So basically all I'm going to do when I see something like this with the denominator of 12, which is almost always going to be the case, is I'm just going to try to break up 5 over 12 into two fractions that can reduce. So, for example, I'm going to say 5 over 12 is the same thing as 2 over 12 plus 3 over 12. And the reason I want them to reduce is when I do that, 2 over 12 becomes 1/6. 3 over 12 becomes 1/4. And now I have unit circle angles that I can deal with. So I'll apply my angle sum formula for sine. So that's sine of pi over 6 times cosine pi over 4 plus cosine of pi over 6 times sine pi over 4. Then I just go to my unit circle. So cosine of pi over 6 is 1/2. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 6 is root 3 over 2. And sine of pi over 2 is root 2 over 2. So that's going to give me root 2 over 4 plus root 6 over 4, or root 2 plus root 6 over 4. Okay. All right. Same idea here for number 6. So I'm going to try to think of 17 over 12. I'm going to break that up into two fractions, where each of those two fractions will reduce. So looking at 17, you might think 15 and 2. That would be okay. You could do 12 and 5. That would be okay. Or, no, 12 and 5 wouldn't be okay because 5 doesn't reduce with 12. I'm going to do 8 and 9. Feel like the easiest ones to me. But there's lots of options. So tangent of 17 pi over 12 is going to be tan of 8 pi over 12 plus 9 pi over 12. So 8 over 12 reduces to 3/4. I'm sorry. Try again, 2/3. 9 pi over 12 reduces to 3/4 though. So when I apply my formula for tangent, I have tangent of 2 pi over 3 plus tangent of 3 pi over 4 over 1 minus tangent of 2 pi over 3 times tangent of 3 pi over 4. So then I go to my unit circle to look up these values. So tangent of 2 pi over 3 is going to be root 3 over 2 over negative 1/2, and root 3 over 4, or I'm sorry, tangent of 3 pi over 4 is root 2 over 2 over negative root, I'm sorry, hold on one second. Yeah, okay, y over x, okay, yeah. Negative root 2 over 2, then 1 minus. Now I've already done this, so I'm going to just copy this down. And we've already done 3 pi over 4. So I'm just going to copy that down. Okay. So here, the divide by 2's cancel, so I'm left with negative root 3. Here, both those things cancel, so we're left with minus 1. And then here, negative and negative, so those will cancel out. The divides by 2 cancel. And then all of that cancels. So I'm left with just 1 times root 3. Just root 3. So there's that. Now typically we don't like to leave a radical in our denominator, so we want to rationalize this denominator. But to do that, since this is a expression involving addition or subtraction, we actually have to do something a little bit sneaky to rationalize that denominator. We're going to multiply by what's called the conjugate. So the conjugate is the same expression, just with the different sign in the middle. So that's how we do this. So in the numerator, we have to FOIL this out. I'm going to get negative root 3, and then negative 3, and then negative 1, and then negative root 3. The denominator, that's just the difference of 2 squares, so I end up with 1 minus 3. So if I combine like terms, I end up with negative 4 minus 2 root 3 over negative 2. And if I reduce that, I end up with 2 plus root 3. So again, nothing tricky there. The worst part is like dealing with all the little simplifications and stuff. So that's that. The easier type of problem, even than those, which are not too terrible, are these ones where we just want to rewrite as a single trig expression. So the way I'm going to think about this is I notice that I have like sine of A times sine of B minus cosine of A times cosine of B. If I go and I look at my identity, that is exactly the angle difference formula for sine. So 47 minus 23 is 24. Again, same idea here, A's and B's. If I look at my tangent formula, this is the sum for tangent. So I have tan 33 plus 26 or tan 59. Again, I'm going to think about these as like A's and B's. So this is the difference for cosines. So this is going to be cosine of A plus B. The only catch here is now I have to make a common denominator and do all that jazz. So this becomes 15 pi over 35 plus 7 pi over 35, which ends up as 22 pi over 35. But that's really kind of as bad as it gets. You're just kind of searching to find what identity can be used to compact that all down. But that's not a lot of work to do there. The last couple we're going to do are proving some identities. To do these identity proofs, some of these we could do using the identities from before, but I'm going to default to using these new sum and difference identities. So in I, I'm going to work on the left side. I'm going to use the angle difference identity. So I have cosine of x times cosine of pi over 2 plus sine of x times sine of pi over 2. Now pi over 2 is an angle on the unit circle, so I can look that up. If I go to the unit circle, cosine of pi over 2 is 0. And sine of pi over 2 is 1. So that cancels out, and 1 times sine is just sine. So we're done. Not too bad. Same idea here. So this is an angle difference for sine. So I have sine of x times cosine of pi minus, sine of pi times cosine of x. So cosine of pi, again, is a unit, pi is a unit circle angle, so I can look up cosine of pi in the unit circle, that's -1. Similarly, sine of pi is a unit circle value. I look up sine of pi, that's 0. So that just kind of goes away, and I'm left with -1 times sine x, or negative sine x, which is what I needed. And I'm done. So these have been so far quite straightforward. What's a little bit trickier is this one, I. So one thing I'm going to notice here, if I look at, I'm going to work on the left side anyways. One thing I'm going to notice is I have 2 x's and x's. So here I see a 3x. I think the obvious thing to do would be to break this up as 2x plus x. So I'll apply my angle sum formula for cosine. So it's going to be cosine 2x times cosine x minus sine 2x times sine x. And I have plus still that cosine x there. And then we have to pull some tricky stuff here because it looks like we're kind of stuck. So the tricky thing is this piece. What I'm going to do with that piece is I'm going to, instead of writing as cosine x, I'm going to write it as cosine 2x minus x, so that I can use the angle difference formula for cosine. And I kind of knew to do this because again, if I look at what I'm supposed to get, I have one of them here. Somehow this has got to cancel out altogether. And this thing has to change. So I knew that, there's no signs in my answer. That part has to go away. The only candidate was that extra cosine x at the end that I had to do something with. Anyways, so when I apply my angle difference identity, I think it's cosine 2x times cosine x plus sine 2x sine x. And those guys cancel out. Then I add those two together. And I have exactly what I need. And I'm done. Okay. So the last thing that we'll talk about here are these double angle identities. So we'll derive one of them, because after you've derived one, you kind of get the idea. So sine 2u, all we need to do is think about this as sine of u plus sine of u. We apply the angle sum formula for sine. So that's sine u times cosine u plus sine u times cosine u, which adds together to give us 2 sine u times cosine u. And that's it. That's the identity. And you could do that for sine 2x and tan 2x. The tan one gets pretty hairy, but we're not going to worry about doing that. I just want to give you an idea of where those are coming from. So those are the double angle identities. So at this point, if you were wanting to do Chapter 6 homeworks, you are well equipped to do 1 through 6 and 7 through 12 and probably through 20, although there may be one where you might want to use a power reducing in there, but I kind of doubt it. We haven't talked about those yet. But I think everything will be okay there. We haven't talked about solving yet, so don't worry about those, although you could certainly do them with what you know about from last chapter. The trick is to just use the angle sum and difference and double angle formulas to break it down so everything has an x in it, so you don't have to worry about doing some of the tricky stuff we had to do last chapter. And then the rest of these things, I think, are pieces that we have to deal with a little bit later. If you're just worrying about working on the Chapter 6 test, which is fair, you could certainly do questions 1 and 2 at this point. We're not ready to do 3 and 4 or 5. You probably have enough to do 6 at least one way, and enough to do 7. Yeah, that should be okay. And you definitely can do 8. 9 you would not, unless you've read ahead about the power reducing or half angle identities. So the last pieces that we have to talk about here in Chapter 6 that we'll do next week, we have to talk about these power reducing and half angle identities, and then talk about some solving examples and some proving identity examples. Okay. Have a good day. And again, if you end up with Chapter 5 questions that you want to talk to me about before the test, certainly stop by and see me during commune time tomorrow or whatever. Okay. Have a good day. Bye-bye.